All right, I think it's going.
Any questions about that which you just did?
The math is so simple. The math is like extremely simple, the most simple math you can get. What would you suggest, like, to understand the definitions more?
Didn't read it.
Yeah,
There are a number of videos out there that should be posted under, I think, videos to watch. Hewitt's come out with a number
there.
of videos with basically to go along with the textbook.
Yeah,
So it depends on what level you're on. So if you're at that level, then the Hewitt videos I think work nicely.
okay.
If you have a better understanding of it and your math's better understanding of it, then you've got the videos that I've done.
Mm-hmm.
And also under supplemental, there should be online resources,
That extra one, yeah, I've seen those.
and that's got a whole mess of stuff.
Okay.
Some good, some bad. The ones that I had watched, I have reviews next to. Others, if you watch one and think, oh, this is great, just let me know which one it is.
Okay.
All right. At this point, some of you know what work is. It doesn't actually have to be capitalized. What is work?
Force times displacement.
And officially, the multiplication is a dot product. Hewitt just, I think, does force times distance, so he assumes force is always going to be in the direction of motion. Energy. What are now, one of the questions I asked on there is what are the three types? I'm pretty sure I did not cover the third one. So what are two of the types of energy?
Kinetic.
The third type?
Mechanical.
Combined, these are mechanical, it's not a third type, but, excuse me, a combination of these. I don't know if Hewitt actually defines mechanical. At some point he talks about mechanical energy, but it's just whatever the kinetic is plus the potential. Yeah, rest, you know. So I guess it was the other class that I had not mentioned rest yet. What is rest energy?
It's like
You got it.
formula.
Yeah, that pretty much is the formula. All right, let's think
E
about,
equals MC squared.
what's that?
E equals MC squared.
Yeah, I'm gonna modify that slightly, but that's the essence of it, equals m sub 0 c squared. And the only difference between m sub 0 and m is that it turns out that as an object gets faster and faster, the mass increases. Part of that answer, part of that statement is generational. Yeah, that's a special relativity thing, and we don't have to worry about that as we start getting closer to the speed of light. So if I have an object that's traveling 30 million meters a second, at that point, we'll start to worry about the difference between m sub 0 and m. So, it's there for completeness. Kinetic energy. Now I know all of you know the formula, but do a quick look because I'm about to ask what the formula is. I'm hoping for the chorus of angels. All right, everyone got it? let's leave it. Oh, no, still looking. What happened? Squared.
I know something squared.
Right, Leslie, mine was.
Big on top.
Become like dad, dropping consonants. All right. Monica has, or as I just said, Monica.
That works.
What's the formula for kinetic energy?
1/2 mv squared.
There are some closed mouths back there, so incredible ventriloquism, or we didn't get quite the course of inches I was hoping for. And I am serious. Everybody, what's the formula for kinetic energy?
1/2 mv squared.
All right, formula for potential energy? Yep, Isabella, say it again?
Which one?
Yeah, and so it varies. The one that we will use the most, the one that is used in, that Hewitt used the most is the one associated with the weight. So every conservative force has a potential energy formula. So if we're talking about weight, this is mgh plus a constant, although the constant's usually ignored. And we're talking about the generalized gravitational force. This is negative big G, mass 1, mass 2 over R. And I believe that we used that at the end of the last one to figure out what the short field radius is, in other words, the size of a black hole, or how massive does an object need to be, or how small does an object need to be to create a black hole. And then the other one that we did was the ideal spring or elastic material, where the force is negative K delta X, and the formula. It looks a lot like the kinetic energy formula, but it's not. Plus a constant. Plus a constant. We got through the ski problem, I believe.
So the last one is the one for potential energy?
These are all formulas for potential energy, depending upon what the conservative force is. So on the last page of the handout, I basically, it's this device as I mentioned earlier. And so the question is, it has issues. But for the most part, if I pull two back, I get two shooting off that way. And the question is why? Because if I do one, only one goes out. So let's take a look at that. It is going to require some calculations. I'm going to simplify it. Instead of having them swinging like that, I'm just going to have them moving along the line. So I'm going to start out with, black on black. There we go. I have an object moving to the right, and I'm going to make this simple and give it a mass of 1 kilogram, just to make the math easier. And I am going to have it traveling at 60 meters per second. Is that going to come back to bite me? It'll make half of it easy, half of it hard. It's going to run into 4 objects of the same mass. So the total here is 4 kilograms. What I want to do is figure out what is the total momentum before the collision. What is the total initial momentum?
Five kilograms?
What'd you get?
5? 1
Nope.
plus 4? No.
That'd be the total mass.
Oh.
Total initial momentum. I think at this point, all of you are well versed on the equation for momentum.
say 60 kilograms per meter per second.
Yeah. It's the momentum of this plus the momentum of that. Well, that's not moving. So that momentum is 0. So that's, all the momentum is right there. That's mv. So I have 1 kilogram times 60 meters per second. And let's just make this simple and say that to the right is positive. So I get 60 kilogram meters per second, or 60 Newton seconds, whichever one you prefer. Or Descartes if you want to define it. Questions on why the initial momentum is 60 Newton seconds?
Because the initial equals
So that's got to be the final. All right, let's see what combinations will get us this and why I chose 60. Yeah, I think that's the smallest one that'll work. So afterwards, suppose I have 4 that stay still, and I got 1 shooting off to the right. And then we're gonna do, I have 3 that stay still, and I have 2 shooting off to the right. And then I have 2 that stay still, 3 shoot off to the right. 1 stay still, 4 shoot off to the right. And we'll end it there. We could do all 5 of them and move on. So these are the possibilities. I got 1 coming in, how many leave? We know that the first one is the one that's more likely to happen. And what we're trying to get to is why. All right, so momentum. I know the total momentum is 60. How much mass is moving after the collision in the first situation?
1 kilogram.
So that's going to be equal to 1 times V final. So what's the final velocity?
60.
Yeah. Meters per second. And by the way, 60 meters per second is roughly 130 miles an hour. Now, if I had the second scenario here, I have 3 that stay behind and 2 go shooting off. How fast do those 2 need to be going? So I know the total is 60. What's the mass now moving?
2 kilograms.
So what is the final velocity? If I have 2 going off, what would the final velocity be?
30 meters per second.
So I get momentum is conserved if I just have 1 shooting off at 60 meters per second, or 2 shooting off at 30 meters per second, or in the case of 3, let's set that up. 60 is equal to 3 V final.
20 meters per second.
In the case I have 4, I have 60 equals 4 V final. So V final. All right, so we have 4 different scenarios here. All of them are indicating that momentum is conserved in each one of those cases. Well, we started with that assumption, and we came up with different velocities depending upon the situation. But still, the first one is the one that seems to happen. So questions on how we got those velocities before we talk about why these 3 tend not to happen. All right, let's take a look at kinetic energy. The initial kinetic energy, we all know the formula. So I got 1/2 mv squared. So beforehand, when I just had 1 coming in, what is the initial kinetic energy? Like 1 times 60 squared. Technically plus 1/2 times 4 times 0 squared.
Why are we doing the 1/2 times 4 times 6?
Why are we doing the 1/2?
Yeah, times 4 times 0 squared.
Oh, because I have 4 objects not moving.
Oh, yeah, yeah. Okay.
So what is the initial kinetic energy?
1800. Oh, I'm sorry.
Jules?
Yes,
Good job.
also Newton meters, also kilogram meter squared per second squared. Personally, I find joules easiest to write, but you do you. Any questions about how we came up with 1800 joules as the total kinetic energy initially? All right, let's start at the last scenario and work our way up. In the last scenario, so I'm gonna just call this case of 4. I know my formula there. What's the mass that's moving at 15 meters per second?
4 kilograms?
And 15 meters per second squared.
Yes. And that would be 1/2. Oh, no, you're not adding 1/2 times 1 times 0,
Oh,
No.
oh, oh, for the other part?
right?
Plus 1/2 times 1 times 0 squared.
Yeah.
Yeah.
Okay. $450.
Jules?
Thank you.
Joules, sorry.
All right, so that's a whole lot of energy lost. All right, let's try K3. And K, in the third situation, so we're talking 1, 2, 3, this one right here. What's the mass of, that's moving at 20 meters per second?
3 kilograms.
Say it again.
3 kilograms.
So 1/2, 3 times 20 squared, plus 0. Technically, 1/2 times 2 times 0 squared.
600 joules.
Didn't lose quite as much energy. K2. Going through the same process, 1/2 times now the mass that is shooting off, because all the stuff over here, these are all at rest, these stay still while those go shooting on. So I have 2 of them at 30 meters per second. Times
900
oh, yeah,
joules.
getting closer. K1, these are all finals. This is before or the initial. And so now I get 1/2 times 1 times 60 squared. And I get 1800 joules. So what's happening is that I have, if I have 1 coming in and then 1 going off, not only is momentum conserved, but kinetic energy is conserved as well. This is not energy conservation, but kinetic energy specifically. If that is the case, where momentum is conserved and the kinetic energy is conserved, this is the perfectly elastic collision. Now, we didn't have the situation where all of them stuck together. We got closer, but notice that as more and more stuck together, we lose more and more energy. And so in the perfectly inelastic collision where they stick together, that's when we get the most amount of kinetic energy loss.
So when all the balls are moving like this, the same together.
Yeah, one comes in, sticks, and they all swing together. All right, give a moment for people to let that sink in. When they stick together, we get the most amount of kinetic energy loss. I'm about to ask a question related to that. And the question is, where does it go? If I had a ball of putty and I threw another ball of putty at it and they stuck together, I lose kinetic energy. But that energy has to go somewhere.
Does it stay in the second ball of putty?
Excuse me?
Does it just sit in the second ball of putty?
Yeah, as what?
What'd you say?
So it loses kinetic energy. So even in this situation right here, in this situation, if 4 of them stuck together, we'd lose 75% of our energy, kinetic energy. That kinetic energy has to go somewhere.
Doesn't energy turn into heat?
And that's where it ends up going. The two putties, when the putty sticks together, or in this situation here, they'll get a little bit warmer. Kinetic energy, it turns out that kinetic energy is related to temperature. The greater the kinetic energy, the greater the temperature.